This is the story of how Henry Bessemer invented and developed his iron and steel making furnace and the problems that he faced and how these were overcome. The Bessemer converter was the forerunner of the modern basic oxygen steelmaking process, which is still used today to make bulk steel rapidly. To conclude, I mentioned the Caldo process, which was used at the old works of the Parkgate Iron and Steel Company Limited in Rotherham during the 1960s and 1970s. Unfortunately, due to severe mechanical engineering problems, the process was scrapped when British Steel was formed. Who was Henry Bessemer? Henry Bessemer, in full Sir Henry Bessemer, founder of the Royal Society, was born on the 19th of January 1813 in Charlton, Hertfordshire. He died on the 15th of March 1898 in Denmark Hill, London, at the age of 85 years. Bessemer was an engineer and not a metallurgist, and he was a prolific inventor with 130 patents to his name. He invented and developed the first process for manufacturing malleable iron and steel inexpensively, in bulk and without fuel, leading to the development of the Bessemer converter. The development of the Bessemer process is clearly illustrated from the very early experimental cylindrical non-rotating furnace to the rotating furnace that we are all familiar with today. Bessemer's early experiments were carried out in his London works called Baxter House, which was situated in St Pancras. To understand the Bessemer process, it is necessary to review some basic iron and steel metallurgy. There are 5 metals that you need to be familiar with. These are pig iron, cast iron, wrought iron, carbon steel, and alloy steel. Pig iron is directly from the blast furnace and cast into sows and pigs and contains a significant amount of carbon, 3.8 to 4.7%. Cast iron is molten iron from the blast furnace, which is then remelted in a cupola furnace and then poured into either sand moulds or cast iron moulds. It contains a significant amount of carbon and is very brittle in tension. The amount of carbon is between 2.5 to 4.5%. Wrought iron can be classed as pure iron with a very small amount of carbon, less than 0.04%, and with the other impurities removed. It is very tough and ductile. Carbon steel is an alloy of iron and carbon with a carbon content ranging from 0.04% to a maximum of about 1.25%, which is known as high carbon steel. Alloy steel contains, in addition to small amounts of carbon, metals such as manganese, silicon, nickel, and chromium to produce a steel with specific desired properties. For example, stainless steel contains a significant amount of chromium. Bessemer's initial aim was to invent a process for producing wrought iron in bulk directly from molten pig iron without having to use an input of external fuel such as coke or coal. He used a blast of air which produced an exothermic reaction. An exothermic reaction generates its own heat. After Mushet's invention, using the addition of Spiegeleisen, the process was able to produce steel of a known carbon content. The iron and steel making process starts with iron ore being converted into pig iron in a blast furnace. The pig iron is then converted into steel in either an open hearth furnace or a Bessemer converter, or the more modern basic oxygen furnace. The electric arc furnace converts scrap steel into new usable steel. All the processes except the Bessemer converter and the modern basic oxygen furnace use an external fuel input to produce the required heat. For example, the open hearth furnace uses gas or oil, and the electric arc furnace uses vast amount of electricity. Simply speaking, the manufacture of wrought iron and steel making involves removing impurities from molten pig iron and then adding other elements if required. This is what Bessemer's converter was designed to do. Therefore, a more accurate definition of steel is that it is an alloy of iron with a small proportion of carbon, ranging from about 0.1% carbon, which is classed as a low carbon steel, to around 1.25% carbon, which is classed as a high carbon steel. Low carbon steels are mainly used in construction for making large structures such as bridges, and high carbon steels are used for such things as cutting tools where a high degree of hardness is needed. Before the invention of the Bessemer process, steel was made in small quantities, firstly using the cementation process and then the crucible process, which was invented by Benjamin Huntsman in the Handsworth district of Sheffield. Subsequently, there was no steel suitable for structural purpose. Ships, bridges, railway rails and tyres and axles were constructed of wrought iron produced by the puddling process. In the cementation process, bars of mainly Swedish wrought iron were heated for a period of about 6 weeks in contact with charcoal, during which carbon in the charcoal was transferred to the iron bars to form what was known as blister steel. The Huntsman process involved breaking the blister steel bars into smaller pieces and then placing them in a crucible holding not more than 60 pounds or 27 kilograms. The crucibles were heated until the bars became molten and the steel became homogeneous. The molten steel was then teamed into cast iron moulds. For large castings, many crucibles were used. This was a long and costly process and produced steel that was used for making cutting tools, cutlery, springs, and other small parts of machinery. There were many steel companies in Sheffield using the crucible process, and one of these companies was William Jessup and Sons Limited. The crucibles full of steel were very heavy, and a massive amount of effort was needed to lift the crucible pots. The size of the pot was determined by how much a teamer could lift, which was about 30 kilograms. Large-scale steelmaking was not possible using this process unless many crucibles were used to fill a large mould. Why did Bessemer invent his converter? At the time of the Crimean War, the artillery cannons were changing. Spherical balls were being replaced by elongated projectiles. To keep the projectiles running true, they needed to rotate about their longitudinal axis. This was difficult as the cannon bores were smooth. Bessemer invented a new projectile to allow this rotation to happen. Gun barrels at that time were made from cast iron, which was not strong enough to resist the increase in bore pressure required. His new metal had to be produced in bulk, and it had to be relatively cheap to produce. It occurred to Bessemer that it would be possible to give rotation to a projectile when fired from a smooth bore gun by allowing a portion of the powder gas to escape through longitudinal passages formed on the surface of the projectile and then terminating at a tangent to the circumference of the projectile. The gases escaping would act as a turbine and produce a rapid rotatory motion to the projectile. Turning now to the innovative steps taken by Bessemer to realise his aim. His initial experiments were performed at Baxter House using a reverberatory puddling furnace, similar to the more modern open hearth furnace. Bessemer continued his experiments using his open hearth reverberatory type furnace when he noticed something unusual occurring. Pieces of pig iron, which were outside the molten bath, remained unmelted. Further investigations showed that the unmelted pieces or shells were decarbonised iron and had become decarbonised by the furnace air alone. This showed Bessemer that atmospheric air alone was capable of wholly decarbonising molten grey pig iron and converting it into decarbonised or malleable iron. This unexpected result was the start of Bessemer's experimental journey into producing his converter. Bessemer now realised that if air can be brought into contact with the molten pig iron, it would rapidly convert it into malleable iron. To try out his theory, Bessemer designed his first converter. This involved a tube being used to blow air into the pig iron, which was in a fire clay crucible. This experiment was a success, and 10 pounds of grey cast iron was converted into malleable iron in less than 30 minutes. This was a small-scale experiment, and Bessemer's next plan was to use a converter with a larger capacity. This led to the design of a cylindrical converter about 4 feet in height. This converter had 6 horizontal tuyeres arranged around the lower part of the converter. Using an air pressure of 10 or 15 pounds per square inch, 700 weight of molten pig iron was converted into decarbonised malleable iron in about 20 minutes. The reaction was violent, as the carbon and other impurities were removed from the pig iron by the action of the oxygen in the air. To contain the material resulting from the violent eruption from the top of the furnace, which was known as the blow, Bessemer designed another vertical cylindrical vessel, but this time with an upper chamber. As before, the converter had 6 tuyeres placed around the lower part of the converter to blow air into the molten pig iron. When the reaction was complete, the malleable iron was poured into hydraulically operated ingot moulds. After much development, the shape of the converter changed to the shape that we are familiar with today. This converter could rotate about a horizontal axis to allow for charging and pouring. Bessemer's experiments were carried out in 1855. In 1856, with the encouragement of the eminent engineer Mr. George Rennie, Bessemer presented a paper on his experiments to the Cheltenham Conference of the British Association. Bessemer's paper was titled "The Manufacture of Iron Without Fuel." A full copy of this paper appeared in the Times newspaper on the 14th of August 1856. The famous Scottish engineer James Naismith was in the audience and contributed to the discussion. He praised the work of Bessemer, and his final comment was, "All this pointed to results so vast and so commercially important that it was impossible to grasp the full effect it must have both on the iron and steel engineering interests of this and every other country." In the book by Professor J. E. Gordon titled "The Science of Strong Materials," Professor Gordon makes the comment on page 17, "The cheapening and improvement of iron and steel during the 18th and 19th century was the most important event of its kind in history, or perhaps just the most important event in history." Bessemer made a number of engineering improvements to his converter. He quickly realised the advantage of conducting the blow in a vessel mounted on trunnion. There were 2 pivot points mounted on either side, so that it could be tilted and so filled and emptied without the blast on, but without having the metal running down the tuyeres. The blast pipe was designed to come through one of the pivot mounts into the blast box. In November 1856, Bessemer filed patent number 16082 for his invention. A number of steel manufacturers then took out licenses to use his furnace design, but encountered serious problems when using it to make steel. There were three problems with the Bessemer process. Firstly, Bessemer's intention was to produce decarbonised malleable iron from blast furnace pig iron and not to produce steel. Secondly, when the molten iron was poured into moulds, it would not settle down due to the release of large amounts of carbon monoxide from the metal. And thirdly, if phosphoric iron ore was used, the steel produced could not be hot worked without cracking and breaking up. These problems needed to be overcome if the process was to be commercially successful. Problems 1 and 2 were solved by Robert Mushet's invention. He added 5% of molten Spiegeleisen to the iron treated by the Bessemer process, which killed the iron in the moulds and also allowed steel to be produced with a known carbon content. Spiegeleisen was a white metallic ore found in the Rhenish Mountains in Russia. Its composition was 86.25% of iron, 8.5% of manganese, and 5.25% of carbon. A patent was granted to Robert Mushet for his invention on September the 22nd, 1856. This made the Bessemer process an immediate success. Problem 3 was solved by the inventors of the Thomas Gilchrist process. As I mentioned earlier, the metal initially produced by the Bessemer process using phosphoric iron ore was weak and brittle, and ironmasters who had licensed the process from Bessemer reported failure. In 1878, Sidney Thomas and Percy Gilchrist realised that the composition of the converter's lining was causing the problem. The original lining Bessemer used was acidic and worked well with high-quality phosphorus-free iron ore. Thomas Gilchrist invented a basic lining which solved the problem, which allowed phosphoric iron ore to be used to produce steel in the Bessemer converter. The speed of the process was very high, and all impurities were removed in about 18 minutes in both the acid-lined furnace and the basic-lined furnace. As you can see, the basic-lined furnace removed the phosphorus. In both converters, the process had to be stopped at a specific time to produce steel of a specific carbon content. The process was therefore rather difficult to control, and Mushet's invention was critical to resolve this. In 1859, only 5 years after Bessemer's patent was granted, he started a company called Henry Bessemer and Company. The business was in Carlisle Street in Sheffield. His aim was to showcase his process to other iron and steel makers, and also to make iron and steel for customers. Unfortunately, the majority of Sheffield steel manufacturers refused to believe that the quality of Bessemer steel could be equal or better than steel produced by the crucible process. Bessemer's view was that their obstinate refusal to see and judge for themselves, which lost the manufacturers of Sheffield the great monopoly of the steel trade. The works in Sheffield comprised 12 converters, steam-driven tilt hammers, and blast furnaces for making pig iron. The works could produce steel at £10 to £15 per tonne, below the cost of producing steel by other Sheffield manufacturers using the crucible process. From 1859 to 1878, a significant number of companies employed the Bessemer converter. The total tonnage of Bessemer steel production in 1883 was 1.8 million tonnes. 1.3 million tonnes of this was made by the acid process, and 500,000 tonnes using the basic process. Camels of Penistone was one South Yorkshire company that employed the Bessemer process. The works was laid out in a classical style with two converters, a rotary casting pit and a hydraulically operated mould system. An overhead crane was used for lifting the moulds and ingots out of the casting pit. There are some people who believe that Bessemer wasn't the first person to invent the pneumatic process for making malleable iron and steel. They believe that the process was invented by a man named William Kelly in the States in 1851, when his experiments with the pneumatic process started. Having read a report of Bessemer's Cheltenham paper in the Scientific American magazine, Kelly wrote a letter to the journal explaining his claim to the invention. Unfortunately for Kelly, he took out his patent in 1857, which was a year after Bessemer's patent was granted. A full description of this controversy is explained in the book by John Newton Boucher, titled William Kelly, A True History of the So-Called Bessemer Process. He explains how Bessemer heard of the invention and then copied it. Going back to the story of Bessemer's opinion of the need to make gun barrels out of steel rather than cast iron to ensure that the bores didn't wear or explode due to the high pressures needed to fire elongated projectiles, Bessemer came up against the strong opposition to his idea from Lord Herbert, the current Secretary of State for War, and Sir William Armstrong, the famous engineer of that time. Not to be disheartened, Bessemer continued to make forged steel gun barrels, but they were made for the other countries and not Great Britain. For example, the Belgian government ordered a number of barrels from Bessemer. Bessemer's iron and steel was of a very high quality, and tests showed that it was very ductile. Tests were carried out on bars of this steel and showed that bending to 180 degrees could be performed without the bars cracking or breaking. This could not be done with cast iron, which would easily crack at a modest angle of bending. A typical Bessemer plant at this time would comprise two rotating converters with air blowing facilities, fume extraction plant, a rotating casting pit, and overhead cranes for lifting the moulds out of the pit and separating the steel castings from these moulds. To summarise, a section through the 25-ton Bessemer converter shows tweers, windbox, trunnions, shell, and refractory lining. The lining can either be an acid lining using silicon and alumina bricks, or basic using dolomite and magnesia bricks. The air from the blower enters the windbox through one of the trunnions, and then enters the furnace through the tweers. Many engineering improvements were made to the converter over the years. Probably the main improvement was the introduction of a detachable bottom, which allowed the tweer area to be changed when it was worn out. The base had a much shorter working life than the rest of the lining. Bessemer designed a detachable bottom, and so did Alexander Hawley in the States. Alexander Hawley was a famous American mechanical engineer with great expertise in steelmaking. The final design of the converter included a detachable bottom and many other improvements to ensure that the converter worked effectively. The disadvantage of the furnace was the difficulty in controlling the final composition of the steel, as the process was so fast and the conversion needed to be stopped at a specific time, which was difficult to do. This is one of the reasons why the Siemens Martin open hearth furnace replaced the Bessemer converter. This process was much slower and therefore easier to control. The last Bessemer converters in the UK operated at the British Steelworks at Workington. The final cast was made in 1974, after which the converters were decommissioned. One of the converters was moved to Kelham Island Museum in Sheffield and can be viewed at the entrance to the museum. The Bessemer converter has had a lasting legacy on the modern steel making industry. Basic oxygen steel making is a modern method of primary steel making from blast furnace pig iron. Pure oxygen is blown onto the surface of the molten pig iron, which rapidly converts the pig iron into steel. Using modern control methods, steel of a known composition can be made. Furnaces of 300 tons capacity are not uncommon. There are currently 3 such furnaces in the UK, with 2 being in the Scunthorpe Works of British Steel and 1 being in the Tartar Works in South Wales. The plan to close down the blast furnaces at these 2 works will result in these furnaces also being decommissioned. Britain will then be unable to make steel from iron ore and will only be able to make steel from scrap in an electric arc furnace. It is difficult to photograph a basic oxygen furnace in operation. The scale of the operation is massive, as can be seen from the photograph, showing a furnace being charged with molten pig iron at the Scunthorpe Works of British Steel. British Steel plans to close down these furnaces and plans to use 2 electric arc furnaces. One of these furnaces will be at Scunthorpe and the other it is planned to be at Teesside. Another furnace based on the Bessemer principle was the Caldo furnace. The concept of this furnace was first initiated by a patent granted to Anthony Bessemer, Henry Bessemer's brother, in 1858. The steelmaking process involved a rotating reverberatory furnace and oxygen blowing for decarbonising molten iron. The patent number was UK patent number 2207. For nearly 100 years, commercial quantities of oxygen were not available or were too expensive, and the invention remained unused. When large quantities of oxygen became available, the basic oxygen furnace and the Caldo furnace became viable options for making steel. The Parkgate Iron and Steel Company Limited in Rotherham installed 2 75-ton capacity Caldo furnaces in the 1960s on their Aldwick development. The furnaces were top-blown oxygen converters using a cylindrical vessel. During the conversion process, the furnaces rotated about the vessel's axis with typical rotational speeds of between 25 to 35 revolutions per minute. Oxygen was injected via a lance with slag-forming materials added separately. Unfortunately, due to severe mechanical engineering problems, the process was not a success and was decommissioned when British Steel was formed. The scale of the vessels was massive, and removal of the worn linings was an arduous task involving specialist equipment. While one furnace was operating, the other was being maintained and relined. This ensured that production was continuous and did not stop. Let me now bring the story up to date. The move to green steel making means that basic oxygen steel making is being replaced by electric arc furnace steel making. The image shows the electric arc furnace at Parkgate being charged with scrap steel. I've used a number of articles and books for this talk. The main ones are listed here on this slide. Finally, I'd like to say a few words about Ken Hawley. During his life, Ken collected over 100,000 hand tools, which are now displayed in the Hawley Tool Collection. Ken had a lifelong mission to preserve the history and craftsmanship that made Sheffield famous as toolmaker to the world. Ken understood also that to make these tools, a strong steel industry was necessary.